This is a video for Year 12 Physics, looking at radioactivity and particle dynamics. It's a particular question from a past trial paper, which I'm not going to mention for obvious reasons, but I'll jot down what it's about. So suppose we're given this. The alpha decay of uranium-238. Okay, alpha because there's the symbol alpha here. An alpha particle, if you recall, is a helium nucleus. Atomic mass 4, charge 2. He, that's another way to write it. Suppose we're given a question like this. So a uranium nucleus undergoes the following radioactive decay process. And we're given a table. We've got the particle, its mass in atomic mass units, also written as U. I like to write it as AMU, but anyway. And its mass in kilograms. So they were nice enough to give the mass in kilograms as well. So the uranium-238 nucleus has an atomic mass of 238.0507785. Mass in kilograms is 3.954 times 10 to the minus 25. The thorium nucleus, thorium-234, has an atomic mass of 234.043594. And in kilograms, 3.887 times 10 to the minus 25. And the alpha particle has an atomic mass of 4.002603. You just look this up on the periodic table, you find it. It's the helium nucleus, mass of the helium nucleus. Its mass in kilograms is 6.648 times 10 to the minus 27. And it makes sense to have a mass of 10 to the minus 27 because it's smaller than the uranium and thorium nuclei. We're also given that the kinetic energy, Ke of the thorium-234 nucleus, 0.072 mega electron volts. If you recall, mega is times 10 to the power of 6. Okay, so it's a million. We need to show, for the first part of the question, show that the kinetic energy of the alpha particle is 4.2 mega electron volts. And this is worth 3 marks. So we're expecting a bit of work here. So let's do it step by step. Now the mark allocation for this is 3 marks for correctly calculating the kinetic energy. That's 3. Shows some working for calculating kinetic energy. That's 2 marks. And some relevant information, relevant info, that's 1 mark. It's a brief outline of the marking criteria. So we need to use what's given in the table. That's a hint there as to what we need to be doing, using the table of values. So the first step is to work out the mass difference or the mass defect. And the way you do that is you go mass of reactant minus mass of products. Reason why it's the mass of the reactant minus mass of products rather than vice versa is because this is nuclear fission. This is the splitting of the nucleus, the uranium nucleus. And the mass of the reactants is more than, the mass of the reactant, the uranium nucleus, is more than the mass of the products. In this case, the thorium nucleus and the alpha particle. Okay, and this is called the mass defect, and you get energy that's released, okay, from the products. So let's work it out using the table. So the mass of the reactant, the uranium nucleus, in atomic mass units, let's stick with that. It's 238. Let's write it all down. Minus the mass of the products, minus the thorium nucleus, so it's 234. Let's put brackets. Plus the alpha particle, which is 4. Close bracket, okay? Because these are the products, that's why I put brackets, parentheses. If you do the maths here on your calculator, you get 4.5815 times 10 to the minus 3 atomic mass units. That's the mass difference. Let's work out the energy difference. I should say energy equivalence, because we're interested in the energy. So we use the answer from here, from above, 4.55815 times 10 to the minus 3 atomic mass units times, I'll explain why in just a sec, 931.5. Because one atomic mass unit is equivalent to 931.5 mega electron volts of energy. This is given on your data sheet for the HSC, so that's already given. So now that we've worked out the energy equivalence, the energy that's released in the reaction, okay, and that's equal to 4.267666725 mega electron volts. We can then subtract the thorium's kinetic energy to work out the kinetic energy of the alpha particle. Okay, so let's do this, 4.267666725. So our answer from above here, right there. Subtract it from the thorium, because this will give us the energy released by the alpha particle. And we get 4.19566725, and that is equal to about 4.2 mega electron volts as required, because that's what the question asks, and it's nice to end with as required. You're showing the marker that you've answered the question. So 3 marks, I'd give a mark there, mass difference, mark for the energy equivalence, and a mark for the working out here. So this is the total energy released, okay, right there. We've subtracted the 0.072 because that's for the thorium, right? So the total energy, which is from the thorium and alpha particle minus the thorium, results in the alpha particle's energy. So that's the first bit. So that's 1. Let's go to 2 now. 2 is show that the velocity of the emitted alpha particle is equal to 1.4 times 10 to the 7 meters per second. This is 2 marks right there. Let's use yellow. Okay, it's quite straightforward. All we need to use is the kinetic energy formula and rearrange for V. So our starting point is this. So V squared, in other words, is just KE. It's just 2KE divided by M. And hence V is the square root of 2KE over M. Now we need the kinetic energy in terms of joules. So from before, 4.2 mega electron volts, that's for the alpha particle. We need to convert this to joules, and on the data sheet, the HSC data sheet, simply multiply this by 1.602 times 10 to the minus 19, and that gives you an answer of 6.7284 times 10 to the minus 13 joules. We know what M is for an alpha particle. That's the atomic, that's the mass of the alpha particle. We know what K is, we've just worked it out, so we simply plug in. So V is the square root of 2 times 6.728 times 10 to the minus 13, 84, divided by the mass of an alpha particle in kilograms, right? SI units, so 6.648 times 10 to the minus 27. That's given in the table up here, right there. Doing the maths on your calculator, you get 1.4 times 10 to the 7 meters per second as required. Right there. So a mark for the working out and a mark for the answer. Let's do 3. 3 is a bit of an interesting one. Requires a lot of thought. Suppose we have a different alpha particle and it's launched into an electric field between 2 oppositely charged parallel plates. Here's an electric field E vector. It's got an initial velocity, so it's launched horizontally. Initial velocity, V initial, is 4.5 times 10 to the 5 meters per second. Okay, midway, so at position here, midway between the two parallel plates. So suppose the two plates, the distance between the two plates is 0.2 meters. Okay, so hence you'll have 0.1 meters up here, 0.1 meters up down there. Suppose the two plates have a potential difference of 100 volts and they're separated by 0.2 meters. Determine the horizontal distance the alpha particle travels before striking the bottom plate. Now this question may seem complex, but it really just invites some of the fundamental concepts of advanced mechanics, projectile motion, and even module 6 on electromagnetism. Okay, so electromagnetism and projectile motion are two key elements you need in solving this. This is worth a whopping 4 marks. So let's do it. Okay, one step at a time. So we need to work out the horizontal distance. Now, whenever you hear horizontal distance for a moving object, think of this formula. Think of the range. Think back to projectile motion, horizontal distance, right? Horizontal displacement. Delta x is the range, horizontal displacement, horizontal distance. U sub x is the velocity along the x direction, and t is the time it takes to reach that horizontal distance, horizontal displacement. We need to figure out as delta x. So we're given u sub x, that's just simply v sub I. We need t. We need to work out t. Now, because the object is moving between two plates, you've got an equivalence between the equations of projectile motion and the equations of motion in electric field. It's going to do something like this. That's what we're predicting, right? It's going to follow a parabolic trajectory. That's one of the assumptions in motion in electric field. Okay, particles, they'll move in an alpha particle is a positively charged particle. So it's going to repel the positively charged plate and go towards a negatively charged plate. It's going to follow a parabolic trajectory as follows. It's going to hit somewhere as well. Hit somewhere on the bottom here. So to work out t, you need something like this. You need to use s sub y is a half ay t squared. Actually, u sub yt minus a half a sub yt squared. If you recall this from projectile motion, this is the vertical displacement, yeah? Now here, this term goes to 0 because u sub y is 0. It doesn't have any vertical velocity initially. It's only horizontally moving. So we're left with minus a half ayt squared. Let's get rid of the minus for now. That's how we can work out our t. But there's also acceleration here involved. So what I'm doing is working backwards, okay, from the displacement formula, the ranged formula. A sub y, we can work that out from this, Newton's second law. Now the force F can be worked out using QE. So let's start off with working out what QE is first. Now Q is the charge of the alpha particle, which is 2. Now E is also given by V over D. We're given potential difference, which is voltage, V, and we're given distance, D, distance between the plates. Q is 2. 2 times 1.602 times 10 to the minus 19, okay, because the charge of a proton is 1.602 times 10 to the minus 19 coulombs. Helium nucleus is made of 2 protons, 2 neutrons. Times that by the potential difference, which is 100 volts is what we're given, and the distance between the two plates is 0.2 meters. Calculating that, you get 1.602 times 10 to the minus 16 newtons. We have force. We can now work out acceleration in the y direction. So it's 1.602 times 10 to the minus 16 divided by the mass of a alpha particle. which is given in the table, 6.648 times 10 to the minus 27 kilograms. And we get an acceleration of 2.4 times 10 to the 10 meters per second squared. Sanity check, yes, 10 to the 10 is massive because the helium particle is small. Small mass, large acceleration, according to this. Let's now plug into this. S sub y is half ay t squared. And rearrange for t. So t is the square root of 2 S sub y over a sub y. I'm not going to write all of this down. I'm just going to skip some steps here. I'm sure you can plug in and work it out on your calculator. You get 2.9 times 10 to the minus 6 seconds. Happens very quickly, 10 to the minus 6, a microsecond. And hence, we can work out the range. And that's given by u sub x, which is what we're given, 4.5 times 10 to the 5 times the time, 2.9 times 10 to the minus 6 seconds. And you get an answer of 1.3 meters. Okay, so the alpha particle travels a distance of 1.3 meters when it strikes the bottom plate. Okay, as required there. Lengthy question. It's not complicated. It just requires a lot of attention to detail and a lot of application. It's just consolidating your knowledge from modules 5 and 6. Simply consolidation there. And that's how you do this question.